Good morning, all. Myself, Anjana Ismail. Today, I am here to present my final semester thesis work on the topic neurodynamics in high order network. In this study, we are trying to mathematically model neural network and study its dynamical properties. So before going to the topic, I would like to introduce some of the basic terms that will help you to understand my topic more easier. The first one is neurons. We all know what a neuron is. It's the basic building block of our neural network, and millions of neurons interconnected to form the neural system. Here, neurons communicate with the transmission. Neurons communicate with the transmission of neurotransmitters. By the transmission of neurotransmitters, they communicate with each other. So next is dynamical systems. System that has the ability to change its state over time is referred to as a dynamical system. The figure shows the growth of humans, which can be considered as a simple and easily understandable example for a dynamical system. And this characteristic change can be termed as bifurcation. The next term is logistic map, which is one of the most simplest applied examples of dynamical system for logistic map for population growth. And it is represented using this equation xn plus 1 equal to ax into 1 minus xn. And the below figure represents the bifurcation diagram for the logistic map. Here we can see that A is the bifurcation parameter, and with respect to this parameter A, the behavior of the system changes over time. Till A equals to 3, we can see that only one value of x is changing with respect to A, and here this state is on a steady state. And we can say that there is a fixed point. And after A equals to 3, the steady state undergoes period doubling, and then from there, with respect to A, 2 points are changing for x value. That means that is the state of period doubling. With respect to A, there will be 2 values are changing. And after A equals to 3.5, this period doubling again occurs continuously, and it leads to a mesh of points, and that state is known as chaos. So here in this bifurcation diagram of logistic map, we can observe a steady state period doubling, and a chaos region. Now we want to look how neurons act as a dynamical system. We see neurons communicate through neurotransmitters transmission, and when an electric signal reaches a neuron, it causes the neuron to fire. And also, this is known as neuron firing, and also there is a potential associated with each neuron. The difference in the interior and exterior potential of neuron causes membrane potential. These two things changes with the time. Also, neuron exhibit significant spiking and bursting behavior. Spiking behavior means this is the generation of action potential when a signal reaches the neuron. And after the generation of an action potential, there will be a relatively silent period. This silent period is known as bursting. So all these phenomena is exhibited by neuron. So we can say that neuron act as a dynamical system. Now we can see what is a higher order network. We can know interactions are occurring around us. That means from biology to the field of engineering, we can see interactions. In an ecosystem, animals are interacting with each other. In a classroom, students are interacting with each other. In an office, we can see machines operating in that office interact with each other. So interactions can occur everywhere around us, and these interactions occur both pairwise and non-pairwise interactly, both pairwise and non-pairwisely. Pairwise interaction means two elements or only interaction between two substrates. Non-pairwise interaction means more than two elements will be occurring in that interaction. So in the case of neural network also, both pairwise interaction and non-pairwise interaction we can see. And previously there are many models studied for this neural network, and most of these models are based only on pairwise interaction. The below figure shows a neural network model that studied by considering pairwise interaction only. However, most of the real life interactions occurring through non-pairwise interaction. So that means it is that much important. Non-pairwise interaction is that much important in real life situation. And these non-pairwise interactions are called higher order interactions. In our study, we are considering both pairwise interaction and non-pairwise interaction, since this helps us to mimic a real world neural network. In order to In order to represent this non-pairwise interaction, we can seek the help of simplicial complexes. Simplicial complexes means it's a topological structure that can be used to denote a non-pairwise interaction. It can be of the form 0 simplex, 1 simplex, 2 simplex, 3 simplex, and so on. 0 simplex simply means that just one node, or only one particular node 0 simplex refers to. And 1 simplex, there will be 2 nodes, and these 2 nodes are connected using a link. In 2 simplex structure, there will be 3 nodes, and these 3 nodes are connected together. Up to 1 simplex, we cannot see any non-pairwise interaction. From 2 simplex onwards, non-pairwise interaction occur. We can generally say that an n-simplex structure forms n plus 1. N-simplex structure contains n plus 1 nodes, as it is clear from these figures. Now, before going to our mathematical model for neural system, just we can say there are many mathematical models existing for neural system till now. And basically, neurons can be modeled mathematically based on two types, based on system of ordinary differential equation and recurrence equation. System of ordinary differential equations is mainly used for continuous system, and this recurrence equations are mainly used for discrete systems. Here we are focusing on discrete systems, so here we will be seeing recurrence equations. There are many mathematical models exist for neuron models till now, such as Hinmarsh-Ross, Hodgkin-Huxley, Morris-Leaker, Pitzak-Nagumo, Chialvo, Rulko, Ishkevich, and discrete Hinmarsh-Ross models. Here we are focusing on Chialvo neuron model. It is an example for discrete neuron model, and of course it is based on recurrence equations. This model is proposed by Dendy Chialvo in 1995. And these equations represent the Chialvo neuron model. This is how mathematically we can represent a Chialvo neuron model. Here X represents the action potential and Y represents the recovery variable of the neuron at a particular time step N. So along with this Chialvo neuron model, we consider higher order interactions also. And the network structure we consider here is ring star network. It is a combination of ring network and star network. As the figure shows, ring network will be in the form of a ring where the nodes are arranged on the peripheral region. And in star network, there will be a central node and all the peripheral nodes are connected to the central node. By combining these two, we will get a ring star structure. Now, the model we consider here is the smallest higher order ring star network model. As the beginning of the study, we just consider the smallest higher order network consisting of 4 nodes. As the first figure A shows, there will be 4 nodes, 1 at the center and 3 at the peripheral region. And these 3 nodes are connected to the center node. There will be pairwise interaction between each of the 2 nodes and higher order interaction between each of the 3 nodes. Star in coupling strength is represented using mu, and the ring coupling strength is represented using sigma 1, where the higher order coupling strength is represented using sigma 2. So next, these are the network equations. We separately write the network equation for the peripheral nodes and the central node. These are the network equation containing all these 3 coupling strengths and x and y variables. So now our network model and network equation is fixed. Now we want to analyze the dynamic properties of our model. Since this is a smallest network, we can analyze both analytically and numerically. The dynamical properties can be analyzed both numerically and analytically. This now here we have analytically analyzed the fixed point, which is the simplest invariant set of a dynamical system. It can be represented as x star equals to g of x star, where the roots of x star gives the fixed points of the system. The network equation which I showed before can be represented in a general form like this as a function of g, where the fixed points can be derived as like this: x star equal to small x star y1 star up to x4 star y4 star. These are the fixed points of this system. I'm not going deep into the derivation of this. Now we can see the stability region. In order to find the stability region, we need to compute the eigenvalues. And from the computed eigenvalues, we plot this 2D color-coded plot that helps us to identify the stability region. From this, we can identify the stable region and the saddle points. Where stable region means where the modulus value of eigenvalue will be less than 1. Saddle region means there will be a value greater than 1 for the eigenvalue, modulus of eigenvalue. If one of the modulus value is greater than 1, that means 1 saddle region it is. If 2 of the eigenvalues, modulus of eigenvalue greater than means 2 saddle region. Likewise, we have up to 4 saddle region. In this figure, a stable region is marked in red color and one saddle region green color, two saddle region in orange color, three saddle region in brown color, and four saddle region in gray color. There are two figures. The first one is by varying sigma 1 versus sigma 2 by fixing mu at a particular value. The second one is by varying mu and sigma 2 by fixing sigma 1 at a particular value. Now, we had plot some phase portraits and time series to understand the dynamics of the network. These are the phase portraits by fixing K node. It's one of the network parameter at 0.03. The first figure shows a fixed point where all the nodes are represented using different colors. The first node is represented in red color, second node in green color, third node in blue color, and fourth in magenta color. So the first figure shows that at these values, the system exhibits a fixed point, and B is the corresponding time series of A. Likewise, C in the figure C, we can see periodic points, and the node 4 exhibits a quasi-periodic state. And this is the D is the corresponding time series of C. This is E is the chaotic state. All the nodes are in a chaotic state. F is the corresponding time series. G is a closed invariant quasi-periodic curve, and H is the corresponding time series of G. Now we are fixing K naught equal to 0.06. Here the first figure represents a non-synchronized closed invariant curve, and B is the corresponding time series. C represents chaotic state and is moving towards synchronization. Here we can identify that the system is moving towards synchronization. And D is the corresponding time series. Here, all the nodes except the central node is nested inside the central node. That is the first figure represents. All are in synchronized quasi-periodic state and is a nested state. And F is the corresponding time series. In G, we can see a periodic state, and there are period of 15. There are 15 nodes, so we can say that it is a period of 15. And H is the corresponding time series of G. This is the last phase portrait, and here all nodes are in synchronized quasi-periodic state. And the J is the time series of I. Now, after plotting the phase portraits and time series, we can see the bifurcation structure. As earlier I told that this will help us to study the dynamic behavior of the network. Here, with respect to the parameter sigma 2, which is the higher order coupling strength, with respect to sigma 2, we are plotting bifurcation diagram for all of these four nodes. Here we vary the value of sigma 2 in both forward direction and backward direction because this helps us to identify the presence of multi-stability. And here also we observe multi-stability, and because we can identify multi-stability is present here since we can see some points there is only black and no red is mixing with them. So the first blue dotted lines shows that that point is a fixed point because there, with respect to sigma 2, only one value is varying for each of the x values. So that is a state of steady state, or we can say that there is a fixed point. And after that, it undergoes period doubling, and 2 periods will be there. And after period doubling, suddenly that turns to a chaotic attractor. Period doubling attractor turns to a chaotic attractor that can be seen in that 2 chaotic region. And after this 2 chaotic region collide each other and forms a last chaotic region that is seen at the end of the figure. After 0.115, we can say it turns to a chaos. So this is the bifurcation diagram of the for neural network model. And these are the typical phase portraits and time series of those 4 dotted lines shown in the bifurcation diagram. The first one shows a fixed point, phase portrait of fixed point and corresponding time series. The second one shows the period doubling of 2 period and its corresponding time series. Then this is that 2 chaotic state. That means transition to chaotic state, that last chaotic state. And the below one is the last chaotic. It is fully a chaotic attractor now. Now we want to see the complexity of our model. In order to understand the complexity of this system, we can use sample entropy measure. The first one is the bifurcation diagram, and the last one is the sample entropy plot. As sample entropy, a low value of sample entropy indicates low complexity, and a higher value of sample entropy indicates higher complexity. Here, for the fixed point and period doubling state, we have a low complex region, and for the chaotic region, we have a higher complex region. Now we want to know the collective dynamics of our network, and in order to that, we have used certain synchronization measures such as cross-correlation coefficient and Kuramoto order parameter. First of all, we can see what a cross-correlation coefficient is. It is represented by capital gamma. When the value of gamma falls into 1, the region falls into a synchronized region. When it is -1, it falls into an asynchronous region. Here we can see that the synchronous region is denoted in yellow, represented in yellow color. As it moves towards asynchronous, the color varies to red and violet. The white region in the figure shows that the system is diverging in those areas. So here also we have plotted two plots, one by varying sigma 1 versus sigma 2, where mu is fixed value, and the other by varying mu versus sigma 2, where sigma 1 is a fixed value. From this plot, we can see that the system exhibits synchronization, asynchronization, and also at some point the system is, particularly when sigma 2 becomes negative value, the system is diverged. This is the plot for Kuramoto order parameter. Kuramoto order parameter is also another measure for synchronization. When it is represented using capital I, when capital I equals to 0, the system falls into a total asynchronous regime. When capital I equals to 1, it falls into a complete synchronous regime. For any value between this 0 and 1, it varies in synchronicity and intensity. Here also yellow is used to represent full synchronous, just like this cross-correlation coefficient plot. Here also we can see synchronization regime diverging, and in between asynchronous and in between varying those intensities. So these results are published in ARXIV on the higher order smaller strings and network of Chialvo neurons under diffusive couplings. It's also accepted for publishing in the European Physical Journal Plus. Now, after studying the smallest network, we move towards a bigger network consisting of 25 nodes. So this is the network model for 25 nodes. It's also a ring-star network based on Chialvo neurons, considering of two simplexes. Here also we are considering two simplexes for higher order. And we derive the network equations. Here we include the, in addition to the activation potential and recovery variable, here we consider electromagnetic flux also, which is represented by phi. So by considering all this, we derive the equation for peripheral nodes and central nodes. These are the equations. Now, for this also, we have plotted some phase portraits and spatiotemporal patterns. The first one represents, here we consider only pairwise interaction. By putting sigma 2, which is a higher order interaction coupling strength, as 0, here we computed the phase portrait. First one represents the phase portrait. The second one is spatiotemporal pattern. With respect to space and time, it varies. And third one is the position of nodes. Here we can see that all are in a synchronous regime. And fourth plot represents the recurrence relation of these nodes, where that is the distance between these nodes are represented in the fourth figure. Here we consider only pairwise interaction. Now we consider both pairwise and higher order interaction, and this is the phase portrait and other patterns for both coupling strength. The first one represents a phase portrait where we can see that the nodes are arranged as two regime, which is the which shows a period doubling. No, in the phase portrait, the plots are arranged as two parts. The second one is spatiotemporal pattern. Third one represents the position of nodes. Here we can see that this is solitary state. That means almost all of the nodes are in a synchronous region, but somehow it falls away from the synchronous region. This is not a solitary state. And the fourth figure represents the recurrence equation between these nodes. So from these plots, we can hope that maybe higher order interaction in a bigger network may promote solitary state. That we need to study deep into this network, and we can come to a conclusion in that. So now we have reached the end of this section. Here we have considered the smallest higher order ring-star network along with higher order interactions on the base of Chialvo neuron map. Then we understand its dynamical properties where we see steady state or fixed point, period doubling, quasi-periodic state, and also chaotic state. Then we saw synchronization measures and all these things. Here, with respect to a neural network, we can say that fixed point can relate to a state of depression or a coma state in a person. Quasi-periodic state can be related to some sleep disorders or tremors in Parkinson's disease. Periodic state in neural system, it is associated with some certain brain disorders such as Alzheimer's, schizophrenia, and autism spectrum disorders. And the chaotic dynamics represent the ability of the brain to generate and process information. Actually, in neural network, synchronization is not that much efficient system. Always one tries to break the synchronization pattern. And this chaotic dynamic is actually used to represent, is by brain to process and generate information. As future direction, we can see, as I told that maybe higher order interaction promotes altered state. We can see in as a future direction. And also we can implement nonlinear coupling stress. Here we saw only linear coupling stress. For all of these links, coupling stress remains same. So we can implement nonlinear coupling stress as a future direction. Also, this model can be made somewhat stochastic by incorporating noises. So that's the end of my section. Thank you all.